My name is Brad Conrad. I'm the director of the Society of Physics Students and Sigma Pi Sigma, the Physics Honor Society, which is graciously supported by the American Institute of Physics. And I'm extremely proud to introduce today's speaker. Today we have Fred Dylla. Fred Dylla is the Executive Director Emeritus of the American Institute of Physics from 2007 to 2015. Fred ended up at his position at AIP because of a whole slew of different reasons, and I highly encourage you to check out his book, Scientific Journeys, which is also the name of his talk, which he'll be sharing with us today. And throughout the talk today, he'll be describing some memorable personalities and events and historical things that all affected his career choice, its evolution, and in fact, how the physics has unfolded and astronomy has unfolded throughout the broader community. So he'll share a couple of snapshots with us today, and we're really appreciative of Fred's time for doing that. Fred credits his joining physics and being interested in physics to a 1962 issue of the magazine Popular Science, for those that have ever gotten that magazine. And I believe the article was something about the invention of the laser, and it really sparked his interest in becoming a scientist and specifically a physicist. He received his formal training in physics during an 8-year stint at MIT, where he earned 3 degrees because 1 wasn't enough. But they did spread over a broad range of different topics, all the way from low temperature physics to acoustics to even biophysics. And after he finished his stint at MIT getting his degrees in 1975, he accepted a postdoctoral position at Princeton University in the plasma physics laboratory, and he stayed there for 15 years because he loved it so much. And he worked there on designing, building, and operating 3 very large devices for the confinement of high temperature plasmas and the development of fusion energy. In 1990, Fred moved on to Jefferson Laboratory, where he built, where they were building at the time in Newport News, Virginia, 2 large electron accelerators. One was for basic nuclear physics studies, and the other one ended up being the most powerful free electron laser ever built. So that must have been really exciting, and we might even hear about that today. So at both Princeton Laboratories and at Jefferson Labs, Fred really initiated sort of the public discourse between public science and technology transfer, especially into industry, and that's how he became acquainted with AIP. And then in 2007, he became the executive director of AIP and was recruited as the 5th executive director of AIP, which was founded in 1931. During his career at AIP, he oversaw the transformation of AIP's large portfolio of scientific journals that required rapid evolution at the time because all the technologies that were changing at the time, the rise of the internet, editing and the dissemination of these became a really important issue that Fred focused on. By preserving and enhancing this primary source of revenue for AIP, Fred was able to strengthen the AIP programs and as well as interact with his scientific curiosity and passion, and that included work with SPS, which we are extremely grateful for. So during the next 45 minutes or so, Fred's going to share some of his thoughts about science, his travels, and the broader field overall. And I would like to share a little personal thing. He let me know that when he was a child, his bedroom, he called it his private laboratory, and he had all kinds of high voltage electronics and radioactive materials and chemicals. And his parents had no idea what was going on. And I think that is really what helped make Fred the man he is today. So Fred, take it away.
Thank you, Brad. Thank you for the opportunity to talk to all of you in SPS students and SPS mentors and faculty advisors. As Brad mentioned, I had a real love for SPS when I headed up AIP. You students are the lifeblood of our field of science, whether you stay in physics, dabble in physics, go into other sciences, or go into any field. What you're going to learn in science teaches you how to think carefully and question evidence, and that's important for whatever you do. So what I'm going to do is tell you about a book that I published late last fall. This was my pandemic project. You're locked inside. Well, it's time to finish unfinished business. And I'd been thinking about this book for quite a while. And it's a mixture of stories that affected my career. I challenge all of you to think about your career and plan your career, but it's really very difficult to plan your career precisely. I hope you all go into science. I hope many of you go into physics, and you'll find your career will be a series of decisions, and it'll be a series of exposures to events and personalities, and hopefully good mentors that will guide you along the way. And I'm just going to pick out a few things along the way that that helped me in my 50-some year career in physics. So why won't my slides change here? Okay, there we go. I was fortunate to grow up in post-World War II America when there was a huge boom in scientific research and science education because of that thing on the screen there. Do you recognize it? That's the world's first artificial satellite, the Russian Sputnik. And you can find a replica next time you're in Washington. You can go to the National Air Space Museum and see it. It's not a very impressive gadget. It was only about 2 feet in diameter. And it did one thing. It sent around a little radio beep at 1/3 of a hertz. And the battery died in 3 weeks. So it didn't do that for very long. And then it only stayed in orbit for 2 months. But that shiny little globe changed science for the US, and it changed it for the world. It ignited in the US a fear that, oh, we must be behind in the space race, and we must be behind in the missile race. And it became a great opportunity for science education and scientific research. And I and millions of other people just becoming students or going into science benefited from that. The very next year, the US put up its own satellite, of course. It was called Explorer. It actually did a little science. It discovered the Van Allen belts. But that same year, an act of Congress called the National Defense Education Act was funded. And that was the real boost that helped me and millions of other students going into science and in the burgeoning research labs and universities at the time. I was trying to find, since Sputnik was launched in 1957, I was 8 years old, I was trying to find a picture of myself. That's not me, but I probably looked like that. And I had a kid brother, and I probably bossed him around. And we thank Hallmark greeting cards for that. But I, as Brad mentioned, had a bedroom that I filled with every kind of scientific gadget I could get my hands on. And had the EPA been around then, they probably would have classified my bedroom as a Superfund site. So let me tell you about, if you get a chance to read this book, it's got 5 sections. It's an easy read. I call it a B&B book for beach, bathroom, and bedroom. You can pick it up and set it down. It's got a series of short essays that start with events that I found interesting that helped program my evolution in science. And then I go into a section where I talk about mentors that I had directly or indirectly, people that I admired in science. And then there's a section you probably find boring about science policy, but if we don't have good science policy, we don't have good science. And so I urge you to take a look at that. And then there's a section on how one of the most important things we can do in science is communicate it. Communicate it to the people who fund science, and communicate to the people who make decisions on whether science should be funded, and communicating it to people who should know how to evaluate facts. And then the last section is just for fun, if you make it that far. There's a lot of overlap between science and art, and I take you on a little tour of that. So the last 70 or 80 years since World War II gave a big boost to the funding of science, lots has happened. I don't have to tell you about it. You read about it and experience it every day. We think we're pretty smart, but I want to remind you, we're not so smart. some of you may recognize this person. This is Hildegard von Bingen, for the town of Bingen on the Rhine. She lived in 11 centuries ago. She was born in 1099. And something happened to her at 8 years old. When I was 8, Sputnik was launched. When she was 8, she was put in a convent. But over the next nearly 80 years, she founded 3 convents. She wrote 3 major theological studies that impressed the Pope so much that she could tell the Pope what to do. That was not the norm back in the pre-Renaissance Europe. She wrote a treatise on natural science that is still in print. It's called Physica. It's over there on the right. And this was a book about botanical recipes, early pharmaceuticals, minerals, and there's even a little sex therapy in there. This is a pretty interesting lady. She also established a new alphabet, and if any of you have ever heard of her, it's probably through your music school. She invented a new form of music that is still around, and there are 70 compositions that are played by people who enjoy pre-Renaissance music. Unfortunately, it only traces of the 3 convents. There's a statue on the left there, one of them, if you ever go to the Rhine, but it's a beautiful town, and there's a small museum where you can learn about her. And fortunately, her treatise and her music survives. So don't think we know it all here in the 21st century. Let me tell you about another one of my heroes. You recognize this guy, right? Tom Edison. Probably the most prolific inventor in the world. He had over 2,000 patents. He invented the form of how we see motion pictures, the first practical telephone that you didn't have to scream into, and of course, sound recording and the light. Now, he wasn't the first inventor of an electric lamp. He invented the first practical one that lasted. There were 22 other inventors of electric light before him, but he had this stamina to not only invent the light. If you had to pick one invention that changed the world, it's probably that. But he also, over the next few years, invented everything you would need to light a city. So on Pearl Street in New York City, you'll find a plaque that memorializes the first power station in the country. And it was built in 3 years from the invention of his light bulb. And now think about that. You had to figure out how you're going to make light bulbs in quantity, which means you had to learn how to produce a vacuum reliably. He designed steam-powered dynamos to generate the electricity. He put in 14 miles of underground cable. We didn't even know what cable was. We didn't know how to insulate cable. And then when you got to a home or a business, he wanted to sell the electricity for more electric light. And so he designed efficient electric motors so you could be buying power during the day. And all of that required things that didn't exist, like a power meter, like switches, like fuses, like lamp holders. All of that in 3 years. And he financed it himself, and later with the help of J.P. Morgan, a banker. And he had to fight huge political fights because the corrupt city hall at the time, called Tammany Hall, was in bed with the gas companies, and the gas companies didn't want electric lights. So when you talk about how long it takes to think about an idea, put the idea into practice, patent it, and put it into place, I want you to go back to this example of Mr. Edison. And of course, right after this, he founded the world's first large research corporation, General Electric, and its research labs. But he didn't do everything right. It's hard to do everything right. I want you to notice this strange bulb that he's holding here in this photograph. It has a protuberance. And in that little glass protuberance, there is a third electrode. The filament is in here, of course, and he stuck a wire in there, and he found that a current could be drawn from the filament providing the light and that electrode. And he didn't think much of it, but he patented. And he kind of scoffed at other electrical engineers who thought, well, no, maybe we could do something with that third electrode. And I give you an amusing statement that he said. He called academics savants. And he claimed that, oh, he'll leave the explanation of this mysterious electric current observed in his two-wire tube to others. I have never had the time to go into the aesthetic part of my work, but it is, I am told, a very important bearing on some law now being formulated by the bulget head fraternity of the savanic world. That's you, folks. That's what he called academics. Well, luckily there were people who paid more attention to that. The other John Fleming, you may have heard of a John Fleming who discovered penicillin. John Ambrose Fleming took that idea of a third electrode and made the first practical vacuum tube for, it was used for detecting radio waves in Marconi's original radio that made transatlantic transmissions. And it went on to become the backbone of electronics. So Mr. Edison missed that, but luckily Mr. Fleming got it. Now, most of you probably have never seen a vacuum tube, but electronics were dominated by vacuum tubes until the late 1950s when Bell Labs invented the transistor. Even the first computer was driven with vacuum tubes. This is the so-called Colossus computer that was built at a secret location just outside of Cambridge called Bletchley Park in 1943. And if you've seen the movies about Bletchley Park and Alan Turing that have been out in the last couple of years, you've heard about this computer. It was used to break the German Enigma codes. Difficult computer to run. This is how you put data in on this long paper tape loop. I think it had a whole 20 kilobytes of paper tape memory. It had 1,000 simple vacuum tubes, which were the switches. And of course, it's very difficult to get all 1,000 of them to work at the same time. And if you go to Bletchley Park now, you can actually see a version of this computer that was faithfully restored by amateurs. The first digital computer here in the US was built at the Institute of Advanced Study outside of Princeton University, and by John von Neumann. And it's interesting that the Colossus in England was used to help end World War II. The first computer at Princeton had two first applications. One to study the evolution of a thermonuclear explosion, the basis of an H-bomb. So still, you could say it started the Cold War, but it was also did the first analysis of DNA, which was just decoded by Watson and Crick in 1952 at Cambridge. Now, since then, all of you carry much more powerful computers in your hand or in your pocket that carries enough memory to put an entire library or access to an entire library in your hand. So let's switch gears to something very close to where I'm sitting right now. I'm here in Lewis, Delaware, right where the Delaware River empties out into the Atlantic Ocean. And it's the home of 3 lighthouses. It's an important bay. River goes up to Philadelphia and Wilmington. So there had been a lighthouse at Cape May and a lighthouse here called Cape Penelope, and another one on a nasty shoal in the middle of the bay called the Brandywine Shoal. And lighthouses until the early 1800s weren't very helpful, because if you've ever seen an ancient lighthouse, they had a very simple parabolic mirror that you actually couldn't see the beam of light, which is usually a whale oil lamp, until you got a mile from shore. Well, if you're in the middle of a storm near a shoal or a rocky shore, that's not safe warning. And so early lighthouses didn't do much good until Mr. Fresnel came along. Augustine Fresnel was an engineer working for Napoleon, and he invented this lens, which I'm sure you've seen, a Fresnel lens, after his namesake. And it uses a series of overlapping prisms to transmit the light so it constructively interferes. And you get a much brighter beam that spreads out less. And in fact, from a simple reflector to a Fresnel lens reflector, you could increase the visibility of a typical lighthouse more than an order of magnitude. Well, shortly after Mr. Fresnel invented these things, the French side of the English Channel, all the lighthouses were retrofitted, and shipping losses went down a factor of 100. Well, the other side of the English Channel, the British learned this, and they outfitted their side of the British Channel. Same thing, huge increase in safety and decrease in shipwrecks. Well, over in the US at the same time, we had a very primitive lighthouse service that President Monroe established in 1820. And unfortunately, the budget for this lighthouse service was controlled for the next 30 years by a gentleman named Stephen Pleasanton. And it turns out he wasn't very pleasant. He was an auditor by training. And he was very proud that when he was given money from the Congress, if he could give most of it back, that was his claim to fame. And so when lighthouse keepers all up and down the East Coast asked if they could buy Fresnel lenses, and even back then they cost a few $1,000s each in 1840 dollars, he refused until a young engineer did an experiment in this bay. He managed to get one lens, Fresnel lens, and he put it on this light on the Brandywine Shoal, and then he went out in a boat and he went back and forth between the Brandywine Fresnel lens and the Cape May simple reflector lens, and he showed by measurement that the Brandywine light was 6 times brighter, and it used 4 times less whale oil, which is how the light was generated. So that convinced Mr. Pleasanton that he'd be saving money on whale oil, even if he put Fresnel lenses up and down the East Coast. So Mr. Fresnel gave an amazing gift to the world using rather simple physics of light and prisms. Now let's switch back to the 20th century. Some of you may recognize somebody in this picture. That's Richard Feynman, probably the most famous physicist after Einstein. Very good physics teacher, as you probably know. And I want to tell you about probably the most important physics conference ever held in the US. And it was held in 1947 over a weekend. And out at the end of Long Island, there's a little island off Long Island called Shelter Island. And there's a famous inn there that still exists. It's called the Ram's Head Inn. And most physicists, a lot of the teachers that I had when I was in school at MIT had spent time either at the Manhattan Project or at MIT developing radar. So the physics community was largely put to work at the war effort. And when the war ended, physicists were eager to get back to basic research on nuclear physics, particle physics, astrophysics. And an opportunity presented itself to try to get a small group of physicists together and talk about what's been happening in quantum mechanics. And so three people, Frank Jewett, who was a former president of Bell Laboratories, Carl Darrow, another Bell Labs employee, who also was the secretary of the American Physical Society at the time, and Duncan McInnes, who was at the Rockefeller Institute. These three gentlemen decided to organize this conference on this June weekend in 1947. They only invited 24 people, but it included Richard Feynman, and to his right, this is Julian Swinger. These are two young Turks at the time working on quantum mechanics. And of course, the old guard at the time, Hans Bethe, Isidor Rabi, Robert Oppenheimer. The title of this conference was The Foundations of Quantum Mechanics. And what's happening at this table, this is Richard Feynman explaining to his colleagues a new way to describe how the electron interacts that is fully obeying what we knew as quantum mechanics and relativity at the time. His outline of this theory became the basis of what's called quantum electrodynamics. And this still remains the most experimentally verified theory of matter at time. And problem was some of the earlier measurements, they weren't quite agreeing with anomalies in the spectrum of hydrogen that were being measured at Columbia by two gentlemen, Willis Lamb and Robert Rutherford. And these analyses solved that mystery, and in the end generated 3 Nobel Prizes for Willis Lamb, Rutherford, and for Feynman. There's an interesting story about traveling to and from this conference. Most of the group took a bus from New York City out to the end of Long Island. And the bus was, they got halfway out Long Island, the bus was commandeered by the local police and directed into town, and everyone was asked to get off. And it turns out the town had heard that a group of physicists that had helped win World War II for the Allies was coming out to the end of Long Island. And so the whole town set up a big party and celebrated and honored these gentlemen. The way back wasn't as exciting, except for one of the attendees, Hans Bethe, took the train back, and he worked out that Feynman's analysis would solve the problem of this anomaly in the hydrogen spectra called the Lamb shift after Willis Lamb. Now, this conference, the entire conference cost $850. Feynman, through the rest of his life, called it the best conference he'd ever went to. Now, that's a pretty good conference for $850, even putting in inflation. It's hard to beat what happened to physics on that famous weekend. When you talk about spending money for science, a question often comes up, well, why should the public pay for it? One of my mentors when I was at MIT was Professor Victor Weisskopf. He was chairman of the physics department at the time. And I give you a quote from an article he wrote in the 1980s. He said, the total cost of all basic research from Archimedes to the present is less than 10 days of the world's industrial production. And look, it hasn't changed much since then. If people ask the question, well, what's the value in basic research? You can't tell me if there'll be a payoff. Yes, you can't predict a payoff, but if we look what happened to quantum mechanics, it gave us the transistor, it gave us the integrated circuit, it gave us solid state lasers, it gave us efficient optical fibers. You put it all together and you have the technology that allows you and I to communicate right now. So huge payoff for basic research. You look for particle accelerators, that's a field that I spent a lot of time on. The magnet technology allows you to get MRIs at your local hospital. nuclear medicine for detecting cancer. And it was our fellow high energy physicists at CERN who invented the World Wide Web so they could share data, large quantities of data efficiently. So there are many estimates of the return on investment for scientific research. There's no one answer, but the range of analyses go from a factor of 2 to a factor of 10 on dollars returned. So I want to read one other quote from Mr. Weisskopf, because research in science doesn't affect, it affects more than just doing science. He says, fundamental research creates the intellectual climate in which our modern civilization flourishes. It pumps the lifeblood of ideas and inventiveness not only to our laboratories and factories, but into every cultural activity of our time. The case for pure and fundamental research is as simple as that. Every few years, business groups like the Council on Competitiveness or the US Business Roundtable or the Chamber of Commerce or the National Association of Manufacturers or the National Academy of Science looks into the value of research. And it comes down, these studies all come down and say our basic economy, our personal health, as we've learned over this past year, and our security, particularly as we move towards looking at climate concerns, are all dependent on basic research. Here's another one of my mentors. This is Professor John G. King. He's no longer with us. He was my master teacher. You're often told if you study a scientific field as an undergraduate and you go into graduate school, you should go to a different school and find a different advisor. Well, I was so fascinated by this gentleman that I ended up spending 8 years with him. The usual argument for changing is, well, you ought to try a different teacher or you'll try a different field. John had the philosophy that anybody with a modicum of effort could become an expert in a particular field after 5 years. And he changed his field every 5 years. And in the 8 years I spent with him, I learned first low temperature physics, then acoustics, then biophysics. And so I had no reason to change, particularly because he was a master teacher. He was a pretty interesting guy besides being a physicist. He was born in London, educated in France and Switzerland, then came to the US where he lived in New Hampshire. And as a young teenager, he took a Model T and outfitted it with an early public address system and would go around state fairs and rent himself out to politicians. That's how he got his cash for doing his experiments. Often did electrical experiments in his basement, wanted more power, and he would hang big coat hangers across the power line out back so he could take power on the other side of the meter, and would have to explain to the power company why there were problems with the meter or the transformer. He spent his entire career at MIT, from an undergraduate to an emeritus professor till he died at the age of 88. And in addition to his scientific research, he was a master teacher, and he showed that in a variety of ways. In the 1960s, there was a movement that the teaching of physics in American high schools was terrible. Not only terrible, but boring. And a group of physicists, including John, formed a committee called the Physical Science Coordinating Committee. And they came up with new textbooks and films. And you can still find the films if you look up PSAC films on a web server. They've been restored and they're quirky. And John stars in one of the films on linear motion. And he ends the film driving off into the sunset in a Bucati that he restored. I met him my first year as an undergraduate in a course called Project Lab, where he'd sit down with you and he'd ask you well, did you ever wonder about so-and-so? How high a Super Bowl would bounce, or why a piano key makes a certain noise? And you'd come up with a project, and you'd work on that project, design it, build it, and analyze it. That became Project Lab, which is still taught at MIT and several other schools. And over his career, 2,000 students took Project Lab and came up with 2,000 interesting projects. And Oxford University Press published a wonderful book of these laboratory experiments, which were easy to do, and you could learn a lot from them. He then had two other educational innovations. One was called concentrated study. That's now it's not so new. Instead of teaching a course 2 hours a week at two separate times, he would condense the course during, say, a January break between semesters, where you could spend a few hours, do a little lab work, do a little homework, come back in the classroom, and do an entire course in 3 weeks. And he compared how well you learned a new field in that method as opposed to the traditional method. And you can imagine what the answer was. His last project he never finished. He wanted to line one of the long hallways at MIT with something called Carter Lab. And these would be self-contained experiments. You'd walk up to a window, you read about an experiment, and you'd push a button or tab a screen, and you'd watch the experiment play out. He was filled with ideas. I think I owe a lot of my education to just having lunch with him and the students every day. And he'd throw out an idea, scribbled on a napkin, and soon we had a fleshed out experiment. And I had colleagues who would say, ideas did not die when talking to John King, they flourished. When I left him as a young PhD student in 1975, my fellow students gave him a brass plaque that was engraved with the following: you can't expect me to explain every cruddy little phenomena. So he was measured on what we would learn from him. I had another mentor at MIT. Many of you probably recognize this fellow on the right. That's Professor Ray Weiss. He devoted 50 years to the design, building, and operation of LIGO, the first device to detect gravitational waves. And what a remarkable researcher and a remarkable teacher he was. How did he get into doing something as remarkable as that? Well, it happened when he was asked to teach a general relativity course in the early 1970s. And he started to think about the last prediction of Einstein that hadn't been experimentally verified by then. And that was the detection of gravitational waves. And he came up with this gadget. This is the final version. This is LIGO, Laser Interferometer Gravity Wave Observatory. One of two stations that are 4 kilometers long. This one is the one in Washington, is the other one in Louisiana. And it's a big interferometer that would change mirror spacing slightly with the passage of a gravitational wave from an intense stellar event. When he first described such a machine in 1972, no one thought you could build one large enough and sensitive enough to detect gravitational waves, and no one really knew the strength of gravitational waves from various astronomical events when all of this was first proposed. But he stuck to it. From that 1972 report, 20 years later, he got enough money from with a group of scientists at MIT and Caltech to build these 2 observatories. It's about $250 million in 1990 dollars. And the surprising thing is, at that time, it was pretty well thought that this machine would not be sensitive enough to detect known gravitational wave sources. And they were right. In the early 2000s, the facility was shut down and upgraded. And in September of 2015, when the upgraded device came online, they detected gravitational waves from two colliding black holes that were about an event that happened about 1.4 billion years ago. And it's interesting that this happened close to the 100th anniversary of Einstein's presentation of his general relativity to the Prussian Academy, which was on November 25th, 1915. So since that first observation, this facility and a sister machine in Italy called Virgo have detected more than 50 black hole collisions. And in 2017, a neutron star collision. And that collision was detected in a way that the LIGO astronomers could tell the rest of the astronomy community to go look in a certain direction because they had 3 devices that could triangulate. And more than 50 different telescopes looked in that part of the sky and saw optical signals from this neutron star collision. And those optical signals had the first hint of spectra from elements heavier than iron. And up until that event, astronomers and cosmologists had no good theory of where elements heavier than iron were made. We knew elements heavier than hydrogen could be made in supernova, but not heavier than iron. So that launched a whole new field of astronomy called multi-messenger astronomy that we now involve gravitational wave detectors along with electromagnetic radiation detectors from gamma rays through infrared and radio. For Ray's work, he was given the Nobel Prize in 2017 with Barry Barish, who headed up the scientific collaboration for LIGO, well over 1,000 scientists, and Kip Thorne, the theorist at Caltech, who did all the early predictions on what sort of gravitational wave event could you get from colliding black holes. Ray's now 87. He's still working 6 days a week. I'm collaborating with him to make a 10 times bigger LIGO, make it 10 times longer with these arms. That, of course, if you don't do it smartly, it's 10 times more expensive. So my field of expertise is ultra high vacuum. So this machine is mainly a big vacuum pipe with a very expensive laser in it, but the vacuum pipe drives the cost. So my dabbling in science is a result of a 50-year relationship with this wonderful mentor, Professor Weiss. Now, I'm going to conclude my talk with something that also happened in 1915. Okay, that was an exciting year for science because of Einstein's general theory of relativity being released. It was also a very exciting year for art. And I want to take you back to the New World. The first art colony in America was founded in 1899 at the very tip of Cape Cod, Provincetown. At the time, it was a Portuguese fishing village. And this art colony attracted the best of the American art community at the time, and it was starting to attract European artists. And, if you were an artist of note, it was a pretty nice lifestyle. You maybe had an apartment in New York, you spent your summer in Provincetown, and then you went over and spent the winter in Paris. Well, 1914 ended that with World War I. And a small group of artists ended up spending the winter of 1915 and 1916 in Provincetown. If any of you are in the northeast part of the country, you know it can get cold and windy. So you're inside, probably doing art and thinking about art. And one of the art forms that this group of artists worked on were woodcuts. Some of you have seen woodcut prints. It's actually the oldest art form known. It was used by the Chinese in the 3rd or 4th century. And of course, in the first printed books, the art was printed using woodcut blocks. The Japanese perfected this technique in the 18th century. You've probably seen a very famous Japanese woodcut called The Wave by Hokusai. These were very laborious prints. You had to carve a wood block for every color. And so a typical color wood block print might involve 10 or 12 wood blocks. Well, this group in Provincetown loved how woodblock prints looked, but they didn't like the fact that it took so much time. So they invented something called the white line woodcut. And here is one by an artist by the name of Blanche Lazelle. And this is a beautiful scene of the Provincetown Harbor. And you can see it's multicolored. And it was done using this technique of carving a little white line between every shape and then putting paint on the block and then impressing that onto a piece of Japanese rice paper. It's a beautiful technique. I fell in love with it. It had largely disappeared until the 1980s when the Boston Museum of Art and the National Gallery of Art in Washington rediscovered it, particularly the work of Blanche Lazelle. She not only brought this art form to the US, but also she brought Cubism from Paris to the US, but never had any fame for any of that. She died in 1955, typically selling prints like this to tourists to Provincetown for a few $100s. If you can find these prints on the art market now, they go for about $20,000. I discovered the art form about 20 years ago from a colleague up in Provincetown. We were Boy Scouts together in New Jersey. We got reacquainted, and he has taught me the art form. And I find it a perfect way to use the other side of the brain. It has use of color and shapes and geometry, and it's very relaxing. And while you're doing it, you can think about anything, even physics. Well, I want to end with the fact that I wrote this book during the pandemic. And I have to mention that we owe our route out of the pandemic to science. You've seen that vaccines were developed in far less than a year, within a few weeks of the early problems of this respiratory disease being noted in China. The Chinese Academy of Science released the structure of the virus. And since right after that, 300 research groups worldwide got to work on developing vaccines. And there are 30 different vaccines in development and about 6 of them out there treating people. I feel very good at the moment because I have 2 shots of the Moderna vaccine in me. This would not have happened without the world's intense development of basic science in biomedicine, and without the world's international collaboration on getting these vaccines developed. But here's where we can't do it with just science. We need the humanities to make sure people take the vaccine, because there's a lot of vaccine hesitancy in the world. And we need humanities to repair the damage that a year's worth of isolation and economic inequities have caused. To say the least of what it has done for your education, my fellow SPS students. And I'm sure you're tired of staring at screens, and you're anxious to go back to in-person discussions and coffee clutches about science and other subjects that interest you. So I thank you for your attention. You can find my little book at any independent bookstore, or from the publisher, or from Amazon, and I think you'll enjoy it. So thank you for your attention.
Great talk, Fred. Thank you for joining us. We really do appreciate it. And I'm happy to announce we have a ton of questions for you. So I and Michaela will see if we can get through them all. First question, could you say a bit more about how Sputnik affected your view of science?
Well, yeah, great question. First of all, I have to remind you, I was 8 years old. Okay. So I wasn't a regular reader of Science or Scientific American. Probably shortly after that, by the time I was 10, I was reading popular science. But when Sputnik happened, I was fascinated to hear about something that could be launched into space. What kept it up there? What was it doing up there? I think all of you probably got interested in science at some point by just looking up at the sky and seeing what you see and going to planetarium shows. So to think about something that was launched on a man-made rocket and went into orbit and did something up there, and over the next 2 years, we had a slew of satellites that were actually starting to make scientific measurements. And by the early 1960s, we were launching people in space. And so that brought an awareness of the excitement of science to me. I didn't know I wanted to be a physicist until something happened that Brad mentioned. I picked up a copy of Popular Science in 1962 and the article was about the invention of the laser 2 years earlier. It was called The Incredible Ruby Ray. And I read that article and I said, that's cool. I want to be a physicist. I want to learn how to invent things like that and do things like that. And over the next 2 years, I wrote letters to 50 companies begging for $1,000 ruby crystal, which is what you needed at the time to make the only kind of laser that existed at the time, which was a ruby laser. I actually got one from RCA Corporation. They said I could keep it as long as I wanted. I still have it. I should have brought it here so I could show it to you. But that article turned me into a physicist.
And that's fascinating. And maybe that leads into the next question, which is, are there events happening today that you think inspire children as much as the space race did for the generation of the 1950s and 1960s?
Of course, and I probably can't list them all in a minute. So I think the parallel event that comes to me from an 8-year-old staring up in the sky and seeing a satellite go by is staring at the images that modern satellites produce of the Earth, where you can practically see the ocean currents and the clouds and lightning and the aurora and similar views of aurora on the planets. I think anybody seeing these pictures just has to be fascinated by the world around you, and can you be a part of it? On the biological side, the fact that you can see molecules in individual proteins. When I was growing up, there was not a micrographic technique that allowed you to see an atom. You believed atoms and molecules exist. But now we have techniques, and you've seen that picture of the coronavirus. There it is. And that spike protein is what the biomedical community has gone after. So I think there's examples every day that can excite somebody about science and what science could do. Some scientists, and particularly science writers, get cocky and think, oh, well, we know it all. There's nothing left to do. We don't know it all. I think you all know that the protons and electrons and neutrons that you and I are made up, and the photons that are allowing us to see, only make up 96% of the universe. We don't know, we have a name for the rest, dark matter and dark energy, but we have no idea what that is. So there's plenty for you folks to figure out. We've left you lots of problems.
Thank you. Jumping around a little bit, somebody asks, you spoke about how basic research has always been important to the development of our society, and I can understand that. But what about research to test out theories? Like, for example, the experiments looking for axions to understand cosmic events. What is the value that they have to people who are generally not involved in science?
That's a good question. And I don't have a good answer for that one, because you could make a very similar question about the discovery of the Higgs boson in 2012. In fact, the science minister of England in the late 2000s had a contest asking scientists to write him a 500-word essay on who cares about the Higgs boson. Well, the person in the street, the person who's not a scientist, could care less about the Higgs boson. Okay? It's not going to affect everyday life. It's not going to affect the next product. You're not going to get Higgs bosons in a bottle and sell them. Okay, but the discovery of the Higgs boson, if you just look at all the ancillary effects of building the most powerful scientific instrument in the world, the Large Hadron Collider, it gave us reliable superconducting magnets. It gave us reliable high-speed real-time data acquisition systems, and it gave us the web. It paid for itself millions of times over. So we don't actually have to answer the question, well, what good is an axion or what good is a Higgs boson? Because there may be something in answering the next level of the structure of matter that has something practical to it. That's the mystery of science. There's not always an answer that you can predict every time. If we could, it wouldn't be called research.
Awesome, thank you. I'm just going to take over from Brad for questions for a little bit here. So another question somebody had was, why was Edison so against the academic community?
You know, I didn't know him personally. I would have asked him that. I think from what I've read from his biographies, he just thought that they were too elitist. Okay, they wouldn't get their hands dirty. If you've read about what he did to invent the electric light bulb, he tried 2,000 different materials. Okay, he had this perseverance and stick-to-itness. He didn't sleep much. You know, he'd take a little nap in the lab. He didn't eat much. It's not a healthy lifestyle. But I think he looked at the academic community as not wanting to get their hands dirty and do the real work. Of course, luckily there were people in his laboratory who knew the basics of electrical theory and could do calculations and things. So it's fortunate that in addition to his inventions, he invented the concept of the modern research laboratory where you had a team. He ended up having a team of people who involved in the new engineering of electronics, but he also had chemists, and he'd have what we call material scientists, and they all had to work together.
Thank you. Speaking of new discoveries and developing new practices, we had some questions about computers. So did people even know about computers in the 40s and 50s, or was it all a secret?
I'd urge you to read a book by Walter Isaacson called The Innovators, which is it has a nice encapsulation of the history of computing, taking the early days in the 18th and 19th century, where computers were actually mechanical, okay, to the first electronic computers, which were the examples that I talked about, the Colossus computer at Bletchley Park in the UK, and von Neumann's first computer at Princeton. So I think, like many technologies, not much was talked about during the war because it was clamped down, but as soon as the war was over, there was a free-for-all to try to develop electronic computers that could do complicated calculations. Because what computers, if you've heard that term used in stories about World War II, computers were usually largely ladies sitting at mechanical calculators. They were the computers.
Thank you. Makes me think of Hidden Figures.
Yes,
that movie.
that's a good thing to read about, because they call themselves computers.
Exactly. And then speaking of older computers, we had a question: how do you feed paper into computers, or what does that mean?
Okay, so the input or output device of a computer is very important. So the input now is largely you typing numbers into memory. But even in my day, the first PDP computers put together by the Digital Equipment Corporation, DEC, in the 60s and 70s, had paper tape readers. And so you had a machine that would transform a letter or a number into punched holes on a paper tape. And that would get read into a reel, like tape onto a reel with a light behind it that would read off the digits. These were incredibly slow and a very little bandwidth. That input rate, I think I told you, was just 100 bytes a second or something. And you can imagine that the paper tape probably broke often.
Thank you. We had a question about the Fresnel lens. So how much did they help? Twice as far? Maybe just some clarification on that.
Yeah, no, it depends on the terrain, but typically an order of magnitude. So if you had a lighthouse with a simple parabolic reflector, the light was visible about a mile away. And with putting a Fresnel lens, it was 10 miles away. And you can imagine if you're in a storm approaching a rocky coast, there's a big difference between 10 miles and 1 mile.
Definitely. Sorry if we've already asked this question already. Did the Shelter Island group predict any new physics, or did it just explain physics?
I would say translating a curious experimental anomaly, which was an unexplained shift in the hyperfine spectra of hydrogen. Okay, this is just a very, if you look at atomic spectroscopy of an element, it's largely predicted by simple quantum mechanic relations. But there was a little quirky difference between the calculations at the time and what was measured. It went by the name of the Lamb shift. Explaining that just told you that, hey, maybe this theory is close to describing nature, but turning it into a real theory that can now predict how an electron reacts in any environment to a precision of better than, I've forgotten how many digits. It's more than 10 to the 12 digits. So it is the most experimentally verified theory of matter, quantum electrodynamics. So that's not bad for a weekend's worth of work. That's
really impressive. Then we had a question from Jose that said, if you were at this moment, maybe in high school, and knowing what you know currently, would you still embark on a career in physics or science, or would you take another path?
Yes, I'd stay in physics. Physics is still very exciting to me. Let me add to that. Okay, I was a kid who built rockets, and I collected radioactive minerals, and I built high voltage gadgets, and I built a laser when I was 13. But I realized that I'm not going to predict when I'm 12 or 13 what I want to do 5 years later, 10 years later. And I realized that if you studied physics, you could go into any kind of science, and you need physics with any kind of science, whether it's biophysics or climate science or material science. You know, other scientists think physicists are a little arrogant when they say things like that. But I remind them that you can't do any kind of science without a good physics background. So yeah, if I had to make a decision now, if I was 13-year-old Fred, in 2021, I'd still go into physics.
That's good to hear. It looks like we just have a comment, one last comment here. It says Richard Feynman was also an artist, and then there was a link for it. And then he said that there's a bunch of other people, other physicists that are artists as well. You have any comments about that?
Yeah, I think I'd encourage all of you to exercise the other side of your brain. I think the dual exercise helps both sides of the brain. You probably know a lot of your friends who like science who are good musicians. I'm a terrible musician. I love music. I love to listen to it, but I'm tone deaf and arrhythmic. But I'm a not bad artist, and I think the combination goes very well. Feynman was a pretty good painter. He was also a bongo player. Okay, so if you like these stories that I talked about today, they're short little essays, and I have a good reading list at the end of each chapter with references. If you want to know more about the Fresnel lens story, more about the Shelter Island Conference, I've got good references at the end of each chapter.
Awesome.
And I published it as a paperback to keep it cheap, okay?
Which we as students appreciate. If anybody else has any other questions, feel free to put them in the chat right now. Otherwise, I just wanted to say again, thank you, Fred, for joining us. It was really nice to meet you virtually, and I hope I get to do more stuff with you in the future. And I'm sure everybody really appreciated your talk.
I hope to see as many of you at the next PhysCon. When I was head of AIP, I got to go to help organize and go to two of them, the one at Fermilab and then the one at the NASA Space Center. And they were a lot of fun. So I hope to see you at the next one, folks.
Yes, please come. Awesome. Well, thank you guys so much. Everybody have a wonderful rest of your day.